my lab was on ferrofluids and neodymium magnets and the speed at which a ferrofluid is attracted to the magnet. I made a homemade ferrofluid, which ended up being not reacting like I wanted it to, so that's why I ended up doing this experimentation. And it was also more viscous, so it was actually a little bit easier, and this is what ferrofluid is actually supposed to react like. Also demonstrated in the pictures, which mine just became a blob when attracted to the magnet. The purpose of my experiment was to determine how the distance from the origin of a magnetic field affected the speed at which, the velocity at which a ferrofluid was attracted to the magnet. And also I did an experiment on the strength of the magnetic field as well and how that affects it. My hypothesis was that as the distance from the origin increases, the time will increase, and as I also said that the field strength will decrease linearly and the velocity will decrease exponentially. I found out very clearly that the magnetic field does not decrease linearly. It actually decreases as a log function, I believe, where at a certain point it starts leveling out, and I did not understand that. So I found the best reason I could find was that there's a point in a magnetic field called a close field and a far field, and I figured that was the best explanation for it. So the equipment, for some reason, some things are not showing up, is neodymium magnets, which I got 8 of. I have a lot of them, but I used up to 8 in my experimentation. A B field sensor, magnetic field sensor, and a lot of ferrofluid, because each time you use it, I just let it go on the magnet, so that it was basically wasted afterwards. My graphs, this is radius, or the distance from the origin point of the magnetic field versus the time it takes. Or, sorry, this is how, this is the log function, sorry. And you can't really see it, but the first 3 points are actually fairly linear. So those are the 3 points I used to determine the velocity at which the magnet is pulling the ferrofluid. And after that, I was going to try and going to try and calculate the field after a certain point, or before a certain point, but by the time it takes, if I could figure out a ratio, but I could not do that, and also because I could only measure so close, because I found out that the sensor only has such a high reading, and for magnets, when you're closer than 2 centimeters, it will overload the sensor. And besides that, after a radius of 1.75 centimeters, the time it took was over 7 minutes, and I just got impatient a little bit. This is the magnetic field versus the distance. I don't recall why I called it radius. And this is just a quadratic. I forgot to put in the linearized, but all you would have to do is take the distance, do an inverse exponential, and it becomes linearized, which I found interesting considering I thought it was going to be linear in the first place. This is 6 magnets, which, as you can see, compared to 4 magnets, the time it takes for the same distance is greatly decreased. And you probably can't see it, but the velocity that I found is basically the same as well, which I found interesting. For the B fields, once again, it was just moved back a little bit farther. for 8 magnets, which is the top number of magnets I went up to. Once again, I had to end up moving I was able to move the distances farther back, and once again, it's pretty clear that that the farther distances take the same amount of time or less time, even in some cases for some of these, at some of the closer distances for smaller sets of magnets did. And once again, everything just got moved back. The error I did was I just took partial derivatives for the first 3 values that I found the velocity from. And I determined that the closer it was, because I could only click my watch timer so quickly, there was an error in that. There was a small percentage error in the fact that I was not able to place the ferrofluid at specific distances. All of those were errors, and it was clear after this that the closer it was, the higher percentage error there was. And it was also interesting for the error analysis was, first off, friction, which is always a problem, especially with this. Stopping the timer, when I was measuring the B field, the magnetic fields, the sensor could be off of the intervals that I was taking, so that would affect the at reading as well a little bit. I figured out when I was moving the magnetic field sensor around that other objects had a small reading as well, so that interfered a little bit. And when I was doing my experimentation, I was just holding down the magnets at the end of the positions that I was, so whenever I would slightly moving it, I'm pretty sure, a couple of times. So that caused an error. I also found that the amount of ferrofluid changed the speed at which it was attracted, which I was kind of confused by that. And I figured out that completely contrary to what I was believing, because what I understood was each little iron particle inside of the ferrofluid slowly gets attracted and becomes polarized itself and gets attracted to the magnet. I was figuring that the smaller amount, the quicker they would become attracted, and all of them would become polarized, which would increase the time or decrease the time at which it was attracted. I found that it was actually the complete opposite, in which the more ferrofluid there was that I was trying to get the magnets to pull, the quicker the velocity, the quicker the time that it was attracted. And like I said earlier, compared to the ferrofluid that is actual ferrofluid, that is very liquidy, and you can just move it around very easily, whereas the ferrofluid that I created had iron particles and vegetable oil. So it was very viscous, and it would only move around so quickly, so that was it's a bit different than actual ferrofluid. And that was basically my experimentation.
Time for a question?
Ali?
What is ferrofluid used for, like?
Actually, I found out a while back. I do not remember where I found this out, but I found it interesting where they're actually beginning to use it in car suspension, because I'm assuming they use the magnets where you can change the quickness of the reaction time by increasing magnetic field and everything. So you can increase the time, you can increase the suspension by, I'm not entirely sure how they do it, but you can increase the rate at which the suspension expands again, which increases the time at which the car reacts to bumps and everything. Or you can decrease it, which makes it a smoother ride as well, which I found all of that interesting.
If you can do that with a magnetic field, you could do that instantaneously. You could respond to road conditions on the fly.
Yeah,
cool.
But they also, the other problem is you have to change the mode that the car is in, to sport mode, to road driving mode, etc.
Michael, I have 3 questions. First of all, you mentioned the 2 things that went into it. How did you make your Ferrofluid?
I found a process on YouTube that said that it would become like actual ferrofluid, but it was not. I found Micker ink oil, or Micker ink, which is really just small particles of iron shavings, and I mixed that in with a small amount of vegetable oil, which just allows it to become a liquid instead of just small particles of a solid.
Cool. And secondly, could you go back to one of the early graphs where you were looking at field versus distance? Any of those? That one there, yeah. You chose a quadratic.
Yep.
And what deeply troubles me about quadratics is when they go down, they're coming up on the other side.
Yep.
You don't believe that the field goes back up again.
No, I
Okay.
don't.
So I would just suggest that you always consider when you're putting a fit on something whether it would go back up again. And if it would go back up again, then a quadratic's cool. Otherwise, you can't use it.
I thought about that, and the problem with, I was thinking about that, I just could not find another fit that even fit the points very well, so that was my problem.
That's cool. There's a lot of neat physics in how a field falls off, and as you said, there's a near field and far field approximation to it. One of them takes into account the geometry of the magnet because they're really close to it, so it's more complicated, and the far field one would probably be the one that you could match. So maybe if you grab just the last 4 or 5 data points, you could get a fit for those. That would be fun. And then you had a table where you were talking about velocities. Would you pull that up, please?
Yeah.
Is that average velocity?
Yes, the values right here are the average velocities for the number of magnets for the first 3 points, because those are the only ones that I found to be remotely linear. After that, it started to increase exponentially, so I decided not to include those.
Okay, so it's the distance that it went divided by the time, so that gives you the average velocity for the closest run, and then you do the next closest run and the third closest run.
Actually, I found it, you can't really see it on these graphs, but I just took the first 3 points and did a linear fit for them. And the slope of that was the velocity.
So that's radius, that's separation distance, right?
Yeah, I meant to change that. It's not really radius, it's supposed to be distance.
Yeah, I understand, that's fine. Okay, so is that a velocity though? Because it has the right units of velocity, but it's like separation, how time spent to get there changes with separation change, not the time of an individual one getting there. So it's related to a velocity. Yeah, there's a little subtlety there that I'm concerned about too. Okay, thank you, Michael.
Did an experiment on the strength of the magnetic field as well, and how that affects it. My hypothesis was that as the distance from the origin increases, the time will increase, and as I also said that the field strength will decrease linearly and the velocity will decrease exponentially. I found out very clearly that my lab was on ferrofluids and neodymium magnets and the speed at which a ferrofluid is attracted to the magnet. I made a homemade ferrofluid, which ended up being not reacting like I wanted it to, so that's why I ended up doing this experimentation. And it was also more viscous, so it was actually a little bit easier, and this is what So the equipment, for some reason, some things are not showing up, is neodymium magnets, which I got 8 of. I have a lot of them, but I used up to 8 in my experimentation. A B field sensor, magnetic field sensor, and a lot of ferrofluid. because each time you use it, I just let it go on the magnet. The magnetic field does not decrease linearly. It actually decreases as a log function, I believe, where at a certain point it starts leveling out, and I did not understand that. So I found the best reason I could find was that there's a point in a magnetic field called a close field and a far field, and I figured that is the best explanation for it. A fluid is actually supposed to react like, also demonstrated in the pictures, which mine just became a blob when attracted to the magnet. The purpose of my experiment was to determine how the distance from the origin of a magnetic field affected the speed at which, the velocity at which a ferrofluid was attracted to the magnet. And also, I